Today I want to continue our discussion of simple harmonic motion and talk about the pendulum. A simple pendulum consists of a mass at one end of a lightweight cord, and we're going to assume that the cord doesn't stretch and that the mass of the cord is negligible. And then what you do is you pull the pendulum back from equilibrium at some small angle and you let it go. If you do that, it'll exhibit simple harmonic motion. And here is a video or a little interactive lecture or interactive figure that you can use for simple harmonic motion. So I'm going to post this on the website, and what you do is you just pull it back and then you let it go. And you can see that if you've got the length of the string right and the spring constant right, that what you can get is the period of the pendulum and the spring to match. Now in a spring, what happens, of course, is that the spring potential energy 1/2 kx squared, when you give it that initial displacement, gets converted into kinetic energy and then back to potential energy and back again. So it oscillates back and forth. In the pendulum, you have the gravitational potential energy that wants to pull the ball down to the bottom of the swing, and once it reaches the bottom of the swing, it's converted that potential energy into kinetic energy, and it uses that to propel itself back up. Okay? So that's what causes the motion of both cases. In order for it to be considered simple harmonic motion, the restoring force has to be proportional to the negative of the displacement. So for example, in a spring, that force was given by Hooke's law, F is equal to minus kx. Here, what you've got, if you look at it, is that you have a restoring force due to gravity. Now, here's the free body diagram for the pendulum, and you can see that, of course, gravity pulls straight down. But the displacement towards equilibrium is along the arc of that curve. So the force that is along that arc is going to be only a small component of the force of gravity. In fact, it will be given by mg sine of theta, of course, and it's negative because it's down towards the bottom of the swing. So minus mg sine theta is the restoring force. Now, that's not really proportional to theta itself, okay, where theta is the angular displacement. It's proportional to sine of theta. But as long as the angle is small, sine of theta is very close to theta. There's a chart here down at their table, down at the right-hand side, and it plots, shows theta in degrees and theta in radians, and then sine of theta. If you compare the values of theta given in radians, which is the SI unit for angle, and then sine of theta, you can see that they're really, really close together as long as the angle is small. For example, for 1 degree, which is 0.01745 radians, the sine of theta is basically the same as theta to 5 digits past the decimal point. For 5 degrees, it's only off by just a little bit. You get 0.08727 radians versus sine of theta giving you 0.08716. So there's good agreement all the way up to about 10 degrees. Past 10 degrees, the agreement gets worse. So generally we say that a simple pendulum will work, this approximation will work, as long as the angle is 10 degrees or less. So what we have then for small angles is the force is equal to minus mg sine of theta, where that's approximately equal to minus mg of theta. And now if you want to write x as the arc length, which is going to be equal to L, which is the length of the pendulum, times theta, then you can write the force is approximately equal to minus mg over L times x. Okay. Now let's compare that to the stuff in bold on the right-hand side of the slide. Remember that for a spring, the force is equal to minus kx. So if you're trying to make an analogy here, then k is equal to mg over L. Okay. Now let's use the equations that we've already figured out for the period and frequency of a spring, a mass on a spring, because we know they're both harmonic. So for a spring, the period is t is equal to 2 pi the square root of m over k. Now if we plug in k is equal to mg over L, then you can see that you get 2 pi root of ml over mg, and the m's cancel out, and so you get a period for your pendulum of t is equal to 2 pi root L over g. So that gives you the period of a pendulum. And then the frequency, of course, is 1 over the period, and so the frequency is 1 over 2 pi times the square root of g over L. So the pendulum equations and the spring equations, there's a lot of analogies between the two. So as long as you can consider the cord massless and the amplitude of the oscillation is small, 10 degrees or less, then the period isn't going to depend on the mass that you attach to the end of that string or on the amplitude of oscillation. Now that might seem strange to you, especially the part about the amplitude of oscillation. Now, while that does break down at larger angles, okay, and the period does start to depend on the amplitude, if the angle gets large enough, then the period doesn't depend on it as long as the angle is small enough. Let's think about why that might be. First of all, you have conservation of energy, right? So the mechanical energy for your pendulum is going to be the kinetic energy plus the gravitational potential, which is 1/2 mv squared plus mgh. As long as you're neglecting friction, this energy is going to be conserved. Now, if you look at it, at the highest point of the swing, this is kind of a reminder from an earlier chapter that we did on energy conservation stuff. You can say that the height h that you pull the pendulum back to is equal to L minus L cosine of theta. And you can see why if you look at the little illustration right here to the side. Pause it if you need a second to remember. Now at the highest point of the swing you'll have some maximum angle, and at that angle your kinetic energy is 0. And if there's no friction, then that gives you your constant energy. Now, when you let it go, at the bottom of the swing, your height is 0, okay? And so all of your energy becomes kinetic. What that means is that the larger your angle theta, the higher your value of h, so the more the gravitational potential energy. And the more gravitational potential energy that you have to begin with, the faster that pendulum bob is going to be going at the bottom of the swing. So it goes faster if you pull it higher, which explains how you can manage to keep that period constant as long as the angle is not too high. Let me do an example problem for you. So here you have a mass and a string of unknown length oscillating as a pendulum with a period of 4 seconds. So what happens to the pendulum if you do these various things to it, the period of the pendulum? First of all, what happens if you double the mass? And then secondly, what happens if you double the length of the string? Then what happens if you halve the length of the string? What happens if you double the amplitude? And then what happens if, instead of on Earth, you had the pendulum measured the period on the moon? So let's look at the equation. The period is equal to 2 pi times the square root of L over G, and that's 4 seconds. Now, to answer the question for part A, this equation doesn't have mass anywhere in it. So the period doesn't change if you change the mass. So that's the answer to part A. It's unchanged. Part B says, what happens if you double the length of the pendulum? Well, if the equation for the period is 2 pi times the square root of L over G, where L is the length, and you double it, then it becomes the square root of 2L over G. And if you say that 2 pi root L over G is 4 seconds, well, then you can pull out that root 2, and you're multiplying everything by square root of 2. So if 2 pi root L over G is 4 seconds, then it would be root 2 times 4 seconds, which would give you 5.7 seconds when you multiply it all out. So the period would get longer by that amount, by square root of 2. What happens if you halve the length? Well, instead of multiplying by 2 that length, you would divide that length by 2, which means that you would be multiplying by 1 over the square root of 2 times 4 seconds, and that would give you 2.8 seconds, so it would get slower. What happens if you change the amplitude? Well, yet again, the amplitude doesn't appear in that equation for the period, 2 pi root L over G. Nowhere in there. So if the amplitude changes, the period won't change because it has no effect on it. And then finally, on the moon, okay, what would happen if you moved it to the moon? Well, the acceleration here on Earth is 9.8 meters per second squared. That's G. But on the moon, it's about 1/6 that, okay? So it's equal to G over 6. So if you plug in t is equal to 2 pi root L over, and then it would be G over 6. So that means that you would be multiplying by the square root of 6 times your period, and that would give you 9.8 seconds. So it would make the period much longer. So that's all the things that you can play with on that question. Now, we all know that we've been neglecting friction a lot, and of course in the real world you can't neglect friction. It's impossible. So in any real oscillating system, the motion is going to be what we call damped. Damped harmonic motion is harmonic motion that includes a frictional or a drag force. Now if you have a small amount of damping, then it still kind of looks like a simple harmonic oscillator. It's just that the amplitude of oscillation gets smaller and smaller and smaller with every oscillation until it finally kind of comes to a stop. If that's the case, then we can kind of think of this envelope, okay, that's modifying the amplitude of the oscillation as it goes along. But if your damping is large enough, then it doesn't look like a simple harmonic oscillator at all. So instead of curve A, where it still kind of looks sinusoidal with the amplitude just going down, you can also get what we call critical damping, which is basically you pull it back and it goes back really slowly and returning to equilibrium slowly, and it doesn't really oscillate at all. Or you can get over damping, where you pull it back and it takes forever and it never quite gets back to equilibrium. So that's overdamped motion. Let me show you what I mean with a simulation. So here I've got a mass and it's on a spring, but I've inserted it in a liquid. Now what I can do is change how viscous the liquid is, how much of a drag it'll have on it. So if the liquid is low viscosity like water, then it'll dampen a little bit. But if it's something like maple syrup or glue, it'll dampen a lot. So I can change what kind of liquid I've got by changing my damping constant here. So first of all, I can put it to 0, and then there's basically no friction or drag, and I give it a push, and it oscillates, and it's just like simple harmonic motion. So I've got a sinusoidal curve. But now if I increase my damping, let me take it up to about 0.13 or so, and then I give it a push, then what happens is I get that envelope effect, and it still kind of looks like an oscillator, but it comes to rest within a few cycles. All right? If I increase my damping by a lot, okay, now I give it a push, and it eventually kind of comes back to equilibrium. That's more like critical damping. And then if I take it all the way up and I give it a push, oh, it takes forever, and it never quite gets there. Oh, okay, there it goes. There it got there. All right, but it took a long time. So that's kind of the idea of drag and friction. Now the equations that describe this are a little bit more difficult, so we're not going to get into that too much here, and that's all I'm going to say about that, and I'll leave it alone. Now another thing is that there's lots of systems where you don't want damping, like clocks and watches. You want those things to keep on going. Think of a grandfather clock with a pendulum that's swinging back and forth. You want it to keep a steady period, okay? You want it to keep going. So damping isn't wanted there, and you do everything that you can to minimize it. But there are some systems where you do want damping, okay? Like shocks on automobiles, okay? If you didn't have the shocks in the automobiles, every time you went over a bump, your car would just go crazy. So it's really important in some systems and not so important in others. And you just have to know the design specifications for what you're trying to do. There's one other topic here about damping, and that's force vibrations. Force vibrations occur when there's a periodic driving force. And this force may or may not have the same period as the natural frequency of the system. If the frequency is the same as the natural frequency of the system, then the amplitude of oscillation will get a lot bigger, and that's called resonance. So one way to think about this is to think about pushing a kid on a swing. So because it's a pendulum, basically, it's going to have a set period of frequency. The period will be 2 pi root L over G. If you push at that timing, then the kid's amplitude on the swing will get bigger and bigger and bigger until eventually the kid falls out of the swing, I guess. But if you try to push the kid at some period other than that, the kid's not going to go very high. Like let's say that you're trying to push a kid on a swing, push him like that. The kid never goes anywhere and looks at you like you're crazy, okay? So there's a natural frequency to systems, and you want to push or apply a force at that natural frequency if you want the amplitude to get bigger. Now there's some times when you might not want to do that, okay? And I'll show you an example of that in a second, but there are times where it's important to drive. So here is a curve that would describe how the amplitude of oscillation for the system depends upon the frequency that you drive the system. So the sharpness of the resonance peak depends on the damping and what frequency it's at. So here, if you push at that external frequency, that natural frequency of the system, you can see there's a peak. Okay? So the amplitude of the oscillating system here, they're both being driven at resonance, and so their amplitude is maximized if they're driven at that frequency. Now, if the damping of the system is large, then you're not going to see as much of an amplitude response as if the damping of the system is low, which is curve A, and you get that nice, sharp, tall peak. Just like damping, resonance can be wanted, like when you're pushing the kid on the swing, or it can be unwanted. Musical instruments and TV radio receivers depend upon people or the system being driven at its natural frequency. But here's an example of a system where it was a really bad idea to drive it at the resonance frequency, and that's this Tacoma Bridge collapse, which is kind of ubiquitous in physics. Let me show you this video.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Poor dog. So, that's an example of a bad case of resonance. So the winds whistling through that valley were going and gusting at just the right frequency that matched the resonant frequency for that weird torsional vibration of the bridge, and it made the amplitude of oscillation of the bridge get larger and larger until the bridge collapsed. So that's a perfect example of a case where resonance was a really bad idea. Okay, so that's all I wanted to say about that. And that finishes off the lectures for this chapter and for this class. So congratulations, you managed to make it all the way through all of my boring talking. And I'll see you in class.